Hello, everyone. Welcome to the Topological Complexity Seminar of the Applied Algebraic Topology Research Network. Today, our speaker is Michael Farber, who will talk about autonomous motion in a changing environment, fibrations, and reaction mechanisms. Take it away, Michael.
Thank you very much. Okay, so first of all, thank you, the organizers, for inviting me to give this talk. And I should say that this talk incorporates ideas from many people who are in the audience, including Stefan Kurz, who is one of the co-authors of the main part of this talk. So in this talk, I will speak about slightly different approach to autonomous motion, which is more realistic and which is practical, which is relevant to many practical situations. I will start with standard approach. I call it case one. And this approach, what is called robot motion planning, kind of very well-known approach. And in this situation, we have robot which moves in a constant stationary in time environment. And well, this picture shows we have some obstacles which are stationary, and the robot has initial state, the final state, there is configuration. So in this situation, we have this formalization, which is well known, so I will go very quickly, but I need to mention it. So we have the notion of a configuration space. And I know that people in robotics, like Dan Kotichek, who is, I think, here at the audience, people in robotics sometimes say that there is no such thing as configuration space. And I actually, in some sense, agree. But in this talk, I will suggest an alternative, so we will see. So in this situation, when the environment is constant, we have the configuration space, and the motion planning algorithm should be a map from pairs of states to motions, which associate with every pair of states a motion from X to Y. So this is a fibration, and motion planning algorithm is a section of this fibration, and this leads to this notion of topological complexity, which is a homotopy invariant of the configuration space. It admits a homological lower bound, admits an upper bound in terms of the dimension. It is related to the Lusternik-Schnirelmann category, and sometimes it is equal to the Lusternik-Schnirelmann category in the case of a topological group. So this is again this picture when we have a robot which moves between obstacles, and the obstacles are stationary. Okay. This I wanted to mention this example. If we just have n points in our d-dimensional space, and pairwise distinct points, then this topological complexity is approximately twice the number of points, and it depends on the parity of the dimension, and it was calculated very precisely in those papers. And this actually is relevant to controlling multiple drones viewed as a single system, single autonomous system. And I just wanted to mention the joint paper with John Aprea, which is a survey. And this, I mentioned this because this survey paper does not appear in MassSciNet, surprisingly. So I just want to advertise this survey paper. I think it came out last year. So, okay, this was case one. So now let's look at case two. So case two is when a robot moves in a constant environment, but their environment may change from instance to instance. So it means that the environment, so it means that our algorithm will work not for this fixed environment, but for a variety of environments. And this approach is what we call parametrized topological complexity. And this was developed jointly with Dan Cohen and Shmuel Weinberger in those two papers. So in this case, again, like on this picture, we have a robot moving from one position to another, avoiding obstacles, but the obstacles are not fixed. I mean, they're fixed while robot is moving, but in principle, they can be in different positions. So in that paper, actually, we had this sentence saying that imagine that we have a naval commander who directs some submarine in waters populated with mines. But these mines are changed every day. So this commander should give information not only from which position to which position the submarine should go, but also where are the mines today. So this is what is called parametrized setting. And in this case, instead of a single configuration space, we have a variety of configuration spaces, and they are parametrized by the configuration space of external conditions. So for each point of the base, we have this pre-image, which is the configuration space of the system constrained by the external conditions B. And when the external conditions change, this configuration space of our system is moving it from fiber to fiber. So this is a parametrized setting. And in this parametrized setting, in those papers, we kind of analyze this, what is called Fadel-Novert fibration, which is actually description of when multiple robots move in space populated by many obstacles. So obstacles are parameters. Positions of the obstacles are centers of the obstacles are denoted by O1, OM, and the positions of the robot are Z1, Zn, and there's conditions which we require that all these points must be pairwise distinct. So this projection is projection of configuration spaces is just forgetting the positions of the robots, only looking at positions of the obstacles, and the fiber is a pre-image. So I think this is, I'll just skip this. I think people are familiar with this approach. It's already, well, the only thing maybe I should mention, what is parametrized motion planning algorithm? So here we have initial vibration. Just a second. I lost my cursor, so I cannot point anything. I can just say. So we have this initial vibration, and out of this vibration, we form vibration of pairs of states in the same fiber. And we have also this space of path, which lie in the single fiber, motions of the system under fixed external conditions. And we have this vibration capital pi, which associates with every motion the initial and final points. So a parametrized motion planning algorithm is a section of this vibration, capital pi. And this also leads to the notion of parametrized of topological complexity. Maybe I'll skip this because I think people know all this. So maybe there's properties that if we have trivial fibration, that this parametrized topological complexity is the same as the complexity of the fiber. And if we have a principal bundle with fiber connected topological group, then parametrized topological complexity equals TC of the fiber, which is the same as category of the fiber. So in general, this parametrized topological complexity is greater or equal than TC of the fiber. There are some other things which I probably will skip this. Are there any questions or comments? So I just want to say that this theorem is the main result which we proved in those two papers. Parametrized topological complexity of the Fadel-Neuwirth bundle. Again, it is approximately 2n plus the number of obstacles. And there is a sequential generalization of this parametrized topological complexity, which we suggested jointly with Amit Paul. Okay, so now I am at the main topic of this talk, case 3. So case 3 is the following. So we have robot moves in a variable environment, and variation of the environment is not known in advance, but well, it can be known in advance. It can be not known in advance. So this situation is discussed and analyzed in this paper, which is joined with Stefan Kurz and Matthias Pilin, which is on the archive. So, and this situation is inspired by the situation shown on this picture. So we have a car, self-driving car, and it has it senses many other cars around, and it needs to move, avoiding collisions with other vehicles. Even more complicated situation you can see on this picture. You see London buses and taxis and cyclists and pedestrians. And so if we want to have a self-driving car on the street of London, it should know how to behave properly. And it should have this, what we will discuss later in this talk. Well, this picture also shows this situation. So we have robot, which needs to, robot is in black, and it needs to move from one position to another. And these obstacles are in orange, and they are also moving. So this is like in the situation on these pictures, which I showed you. Okay, so so in order to make this work, we need what we call a reaction mechanism. A reaction mechanism is a system, is a kind of way of feedback or reaction on changes of the environment, such that so it will guide the vehicle or the system, the robot. I mean, what I say is applicable, of course, to self-driving car, but it also is applicable to many other situations when you have an autonomous system, a drone or something autonomous, which needs to be consistent with the environment which is changing. So this reaction mechanism should allow the system to remain consistent with the motion of the environment. Well, in the case of vehicle, it means that it should avoid hitting other vehicles, of cyclists and so on. And also this reaction mechanism should help the system to implement its ultimate goal. Okay. So reaction mechanism is a device which solves the tasks A and B. And let's see how, just a moment, I just want to, sorry, I need to make, I don't see my cursor. Sorry, 1 second. Oh, okay, now go back. Okay, can you see my slide? Hello?
Yeah, the slide, I don't see the cursor.
Oh, okay, just the slide. Okay, fine. So reaction mechanism is the following thing. So we have this vibration of the configuration spaces, which is denoted here P from E to B. So it is family of configuration spaces parametrized by the external conditions. So the state of the system is described by a point of the total space of E. And external conditions are a point of the base, which is projection of this E onto the base, so which is denoted here B, which equals P of E point of B. So the external conditions move, and their motion is represented by a continuous curve gamma in the base. And this curve starts at current state of the external condition. A reaction mechanism L, I call it L, associates with the curve gamma and the point E. E is the current state of the system and the external conditions. So L, this reaction mechanism, associates with this gamma, and E associates this gamma tilde, a curve in the total space, which starts at point E and which projects onto gamma. So this is actually what is called in topology textbooks a lifting function. So let's see, what is a lifting function? So if, as standard notation, e to power I is a space of curves in E. And from this space, we have projection pi onto E cross BI. So BI is a projection curve on the base, and in E, it is the initial point of gamma tilde. So a lifting function is a map in the opposite direction. It's a section of this map. So it goes from E cross BI to EI. So it lifts curve on the base. It lifts to a curve in the total space. And so if we have a lifting function, so potentially it may be our reaction mechanism. At least it will solve the problem that our it will give us a lifted trajectory, and this lifted trajectory will be consistent with the external conditions of the system. And we know from Spanier, chapter 2, section 7, theorem 8, which theorem in a textbook says that a map P admits a lifting function if and only if it is a vibration in the sense of Gurevich. Perfect. So what else do we need? We can say we take lifting, so we can sorry, I'll go back. We can say, well, we have vibration. It has a lifting function. Let's take this lifting function and it will serve as our reaction mechanism. Okay. However, well, this is a kind of, it's a little bit wrong what I said. I will just correct myself. So, well, it's not will work. It will not work like this. Why? Because if we look at external conditions, at some point, at some time t, we know what external conditions are up to time t, but we don't know how they will behave further. So our observation is only until moment t. And lifting function, so our lifting function should take into account this property that our information, we know information about external conditions only until moment t. And so our decision at moment t should depend only on this part of the trajectory of the external conditions. This means that this reaction mechanism should be incremental or infinitesimal in nature, and we will discuss this, and this is a main kind of point of this talk. Am I still okay? Are there any questions? Okay. So this is, I call it case 2.5. So it's not exactly case 3. It's case between 2 and 3. So this case is when the variation of external conditions is known in advance. Suppose maybe there are such situations, actually there are such situations, when we know how this external conditions, so how the other cars and pedestrians will move. If we know all this, then we can actually use parametrized motion algorithm, and we will see that it solves the problem completely. So, so this I want to say, actually, this slide. So, John, I'm okay with time? Time is still okay, right?
Yeah, time is fine.
Okay.
You have a lot of time.
A lot of time, okay. So when can we assume that, when can we know in advance how the external conditions will behave? Okay, well, actually, there are situations, and this is explained on this slide. This, as I learned from Stefan and other people from this community, that there is a prediction, there is a block of predictions. I mean, this self-driving car analyzes the motion of other cars and pedestrians and make prediction. So it may predict for short time how the other cars will behave. And this is actually what we do when we drive them ourselves. I mean, when I drive, when you drive, we can look at other cars and we want to understand what they're doing in order to understand what they will do next. And this is exactly this block of predictions. And this block of predictions can give you a prediction, but for very short time, prediction into the future. So we can assume that this happens for short time into the future. Okay, so this is the same picture as before. Okay, so now I want to explain this theorem, which is stated here. that, I mean, if we start with, maybe I'll go slowly, sorry. So we start with a parametrized motion planning algorithm, which is a section of that bundle which I described earlier. So it's a function which associates pairs of states living under the same external conditions, a motion of the system, which starts with one state and finishes at the other state, and the whole motion is under constant external conditions. So we fix this S. It's not continuous, of course, but it has regions where it is continuous. It can be partitioned into continuity domains. And we can fix a lifting function on this bundle. So we assume that our vibration is a Hurewicz vibration, so it has a lifting function. So we fix this L, and out of this S and L, we can construct a modified motion algorithm S tilde, which will work under variable external conditions, assuming that the variation is known in advance. Okay, so this modified algorithm is described as follows. I call it extended algorithm S tilde. So it will take as input triples gamma E prime. So gamma is a path in the base, so it is a motion of the external conditions. E and E prime are states of our system, which are consistent with external conditions gamma at 0. And output of the extended algorithm is a curve which is denoted here tilde gamma, gamma tilde. And this gamma tilde covers gamma. It is a lift of gamma. It starts at E and it finishes at a point which is denoted by L E prime gamma at 1, which I will show on this picture. So let's look at this picture. I'm sorry, I cannot, my cursor is not working. I don't know why. But so this gamma is a curve in the base. Gamma tilde is a lift of this curve by this lifting function L. And this dotted line is lift of this gamma, of this the same curve gamma, but which starts at gamma prime, at our target. So this final point of this L E prime gamma represents the state of our system in this new what happened? Sorry. Go back. Now you can see my cursor. Am I right? Can you see my cursor? John?
Yeah, I can see your cursor there.
Yeah, let me do it like this, because the cursor works in this mode, yeah. So this dotted line is a lift of gamma starting with E prime. And this final point of this dotted line is this what is called, which is called here L E prime gamma at 1. So this is a new location of the system which represents the target state E prime. Is it okay? So this is our extended algorithm. So this extended algorithm, John, can I just use this not full screen mode?
I think so. I can see it fine. If it's not okay with anyone, let us know.
Okay. So so the extended algorithm as tilde is a section of a bundle like this, which I call P tilde. And it's given by this formula. So, I mean, maybe I'll skip this part. What is important here is that this extended algorithm, this is just repetition to what I said before. It's given by this formula. So in this formula, so we see L and S. So it is a kind of, it uses parametrized algorithm and the lifting function, and it gives us the way of controlling our system under variable external conditions, assuming that we know in advance how this gamma will move. So this is another picture which also explains this formula. To explain this formula, there's another picture. So this is the fiber, initial fiber, where we have this initial E and initial target state, E prime. And this gamma tilde, this gamma is a movement of external conditions in the base. So this is the lift, this gamma tilde. So it means that we move distance t along this connecting curve, which is S E prime t. So we get to this point, and then we move along this point time t along gamma. Okay, so this is just picture explaining this construction. So we arrive at the following statement. The extended algorithm has, which I will, no, sorry, I just said we arrive. Next, I want to state the following theorem. The following theorem says that this extended algorithm has complexity equal the complexity of the initial parametrized algorithm S. Okay, so in some sense, it works in a bigger generality. So parametrized algorithm works only when external conditions are constant, but this will work for variable external conditions, but we need to know in advance how they will change. And the proof is here. I'm just curious, should I? Okay, so yeah, I think I have time. So if we look at this formula, we see that if U is an, let's say, open subset here in E to B, such that this S is continuous on this open set, then this the formula will be continuous on the pre-image. So it will be continuous on U tilde, which is the pre-image of this open set under this projection. So if K is this parameterized topological complexity, then we can cover this space E to B by K plus 1 open sets, which with continuous sections of this vibration, and then these pre-images of those sets will form an open cover of this product, which with sections of this bundle pi tilde. And this means that the sectional category of this bundle pi tilde is smaller than or equal to K. But on the other hand, this bundle contains the bundle pi as a restriction on a subset of the constant paths, which implies the opposite inequality. So they are equal. So this is kind of case 2.5. So it is case between case 2 and 3. I think this case actually is important because we, in practical situation, we can use predictions and use this construction to construct motion for short period of time and then reconsider. So this result can be compared to the paper which Mark and Sergei Uzvinsky and we had many years ago, and we were actually really surprised that the topological complexity in the case of moving obstacles is the same as the topological complexity of stationary obstacles. This this theorem, which I just mentioned now, is a parametrized version of this theorem. Okay, so now let's consider. I'm still okay, right? Still have plenty of time. John, are you there?
Yeah, you still have time. I'll tell you when you're running low.
Okay. So now is the main kind of point, main situation, case 3, real case 3, when automated system knows the current state of the external conditions. It knows also its own current state, but it does not know their future behavior. So we don't know how the others will move. We know where they are now. And also, what we can also know is we can not only measure their current positions, but we can also measure their velocities and their accelerations. Everything infinitesimal can be measured by sensing. High derivatives, in principle, can be also measured, but I will not discuss this. So is it okay? So this is the main point. So our decision, I am this autonomous vehicle. I see where I am now. I see where the others are now. I see what is my speed, what is their speed, their acceleration, my acceleration, but I don't know the future. And I make decision for this moment. And my decision is actually my velocity. I choose my velocity for this moment. So this is what we call infinitesimal motion algorithm. So in this first part, case 1, what we mentioned, motion algorithm is a map from pairs to motions. But we see that motion algorithm actually should be, in this situation, should be infinitesimal. It should depend only on the current state of everything, and it produces infinitesimal output, only velocity at the current moment. And then, of course, this can be integrated. So this gives a differential equation, which can be integrated, and it gives the motion. Is it okay? Are there any questions? Okay, so let's see. So we want to formalize all this. So we have vibration of configuration spaces, which is denoted by P from E to B. So it's a family of configuration spaces parameterized by the configuration space of the external conditions. And we assume now that this B is a smooth manifold, E is a smooth manifold, and P, this projection, is a smooth map. We assume now that everything is smooth. By the way, it would be interesting to understand what happens if there's no smooth structure, some polyhedral version. I don't know. I don't know the answer to this, but let's assume everything is smooth. So we have tangent bundle, of E. So all vectors tangent to E, and there's the tangent bundle to the base. And we have this differential of the projection. So every tangent vector to the total space, you can project it. It gives you tangent vector on the base, and they are related by this formula. Anyway, so we have this, what I call P, this fancy P, capital P. It is the following map. It is, so you have a tangent vector on the total space, and you associate to it the point of the total space where it is attached, and also its projection onto the base. Okay, so this is what is written here. It is a pi e of y is point where it is attached, and this is differential of this projection. So this is this map. And now we have this definition, and an infinitesimal lifting function is a continuous map which goes from here to here, which goes from E cross B TB to TE, which is a section essentially, which is a section of this bundle. So infinitesimal lifting function or infinitesimal motion algorithm, it is equivalent terminology, is a section of this fibration. Okay, and this picture shows, so you give me some velocity of external conditions, and E is the current state of the system and the external conditions, and this infinitesimal lifting function produces this Y, which covers this X and which starts with E. Okay? Okay, just a minute. Okay. So we can just restate the purpose of this L, this curly, so it is infinitesimal lifting function, using the language of robotics. So given a state E of the system and of the external conditions, which are consistent with each other, and given the velocity of the motion of the external conditions X, the function L produces the velocity Y of the system consistent with X. So essentially it is the same like here, picture like here, but it's on the language of robotics. I mean, we say with velocity of the motion and so on. So this, so the function, this curly L, produces the velocity of this autonomous system, which is consistent with X, with motion of external conditions. So this, we call this also an infinitesimal reaction mechanism. So it reacts on velocity of change of external conditions, and its reaction is infinitesimal. So once we have this infinitesimal lifting function, then for every regular curve, we can just look at this ODE. So it is ordinary differential equation. So we take this curve gamma tilde. Gamma tilde will be the solution. This is this differential equation with respect to gamma tilde. So this derivative of gamma tilde will be equal to this vector, which is lift of the velocity of external conditions at this point T. and the initial condition is equals E. So this is ODE, this is ordinary differential equation, which gives you a lift of curve, and the solution exists locally and is unique, but it may not exist globally. So we say that an infinitesimal lifting function is complete if the solution exists globally for every pair of the initial, just a moment. And if the fiber of the bundle is compact, then it is always complete. Anyway, so there is a classical construction which is called Ehresmann connection, and it also gives an infinitesimal lifting function, but of special kind. And this is classical. This is called Ehresmann connection, and it is the following. So we have this smooth bundle P, and we have this family of vertical spaces. These are vectors which are tangent to the fibers. These are tangent vector tangent to the fibers of the fibration. So they lie in the kernel of differential. They form what is called vertical distribution. Horizontal distribution is a complementary distribution. Sorry, it is on next slide. An Ehresmann connection for the bundle is a differential distribution which is complementary to the vertical distribution. So this vertical distribution is canonical. It depends only on the projection. But this horizontal is not unique. I mean, there are many choices. And it exists, you can choose it. And this is called an Ehresmann connection. So it's a horizontal distribution, and each, so it is each tangent space, can you see my cursor, TE of E, is a direct sum of the vertical and horizontal, and when you apply the differential, this vertical goes to 0 and horizontal goes isomorphically onto the tangent space of the base. So for every tangent vector of the base, there exists a unique lift y in the horizontal space, which satisfies this, which goes onto x. So this gives an infinitesimal lifting function. So Ehresmann connection defines an infinitesimal lifting function. I think I have to go faster. John, I have 10 minutes left. Am I right?
Yeah, if you could get it down to like 8, that would be great.
Okay. So let me just skip this one. So the point about this Ehresmann connection is that, yes, it gives infinitesimal lifting function, but this infinitesimal lifting function is linear. It's linear with respect to x. So a sum goes to the sum, and if you multiply by lambda, the lambda comes out as a factor for every real factor lambda. So we can state that the infinitesimal lifting function arising from an Ehresmann connection is a linear function, and vice versa. Any infinitesimal lifting function possessing these linearity properties originates from an Ehresmann connection. So Ehresmann connection is a lifting function, infinitesimal lifting function, which is linear. Okay, maybe I'll skip this. No, I'll just, sorry, I'll go faster. So, okay. Are there any questions? No questions. Okay. So, what is the structure of the space of infinitesimal lifting functions? Well, I mean, it's not a linear space. It is a kind of affine space. If you have a function, if you have a function theta, you can make kind of convex combination or affine combination of two two infinitesimal lifting functions. I'll just skip this. So it is not a linear space, but it is an affine space. So we can look at associated linear space of what is called reaction forms. So reaction form is map from E cross TB to the vertical distribution such that if you project onto E, it is identity. It is just a projection. So it means that for every if you have a tangent vector, on the base, it tells you this reaction form, it moves you in the fiber, it reacts inside the fiber. It gives a vector tangent to the fiber at this point, E. Okay. So, and I'm just skipping, going faster. So there is a structure, general structure of infinitesimal reaction mechanism. A general infinitesimal reaction mechanism can be represented as follows. Of course, it's not unique representation. You can choose one Ehresmann connection, L0, it can be Ehresmann connection, plus some reaction forms, and the total will be an infinitesimal reaction mechanism. And typically, these forms are concentrated near the boundary components of the configuration space. So this is an example. Suppose that the fiber of the bundle of configuration spaces is a manifold with boundary. And this is typical. They usually have boundary. Boundary is when they touch each other. I'll come to this example, which I will go very fast now. So if it is a manifold with boundary, we can take a vector field on E, which is tangent to fibers, and it's supported near the boundary. So then we can define this reaction form by this formula. So it pushes away from the boundary on this vector n, and the magnitude is absolute value of this vector x. And you see that this is not a linear function. It is a kind of nonlinear reaction form. This is the picture. So this reaction form kind of pushes our system away from the boundary. And the boundary is actually, you will see in an example, which I will come in the moment. Anyway, let's go on. Yeah, so this lemma is important. I just want to state it, no linear reaction mechanism can implement the task of pushing away from the boundary, and hence non-linearity, which appears here, is unavoidable. Okay, so I have 1 minute. John, is it okay? Example, which is the last section of our paper, which is on arXiv. So everything I say is in that paper. So if I'm too fast, you can find it in that paper. So let's consider the situation when we have two robots, M and N, on the plane. They're represented by balls of radius 1, and M is our system, is our autonomous system, and we kind of think about motion algorithm for M, and N for us is an obstacle, and N moves as it wants to move, so we don't control N. N is moves by itself. So admissible configurations are, the Cm is the center of M, and Cn is the center of N. And admissible configurations are when the distance is at least 2, because otherwise they will collide. And if it is equal to 2, then they just touch each other. Well, so I'm just out of time, so I'm going faster and faster. So the configuration space E is a space of pairs CM-CN satisfying these conditions. B is just a plane, so there are no restrictions. And so this projection is a trivial bundle in this case. So admissible velocities, if these centers are on distance bigger than 2, then there is no restriction. But if the distance is 2, then the admissible velocities must satisfy this inequality. Well, maybe, John, I'm out of time. Maybe I'll just say that it's all in the paper. So there are several, I just want to say that there are several examples of infinitesimal reaction mechanisms for this system. So one is when we just copy the velocity of the other guy. So I decide my velocity will be exactly like the velocity of the other guy. So in this case, if he's moving along some curve, I will just move in a parallel fashion. I mean, I will just copy his movement and so on. There is and this is actually an Ehresmann connection. This is linear. And then there is another example when we call, it's called no reaction. John, I'm finishing. 1 second. Just a second. Anyway, I'll just skip. I mean, there are examples in the paper, and I don't have time. This actual example is important because it also involves what we call actuation function. And there are further examples. I'll just go to conclusions. Conclusions. So first of all, we showed that any parametrized motion algorithm determines motion algorithm for autonomous systems moving in variable environment, assuming that the future behavior of their environment is known. Secondly, in general, one needs to employ infinitesimal motion algorithms, which use only information available at the current time t and generate the velocity of the autonomous system for time t. A most general infinitesimal motion algorithm can be constructed using a fixed Ehresmann connection and reaction forms and actuation functions. So this is general. And then linear reaction forms are not flexible enough. They do not allow push-away maneuvers, and one has to employ nonlinear reaction forms as well. That's it. Thank you. These are 4 conclusions.
Okay, unmute yourself and thank our speaker.
Thank you.
I don't know what that is. Oh, I guess. Are there any questions?
Is it possible to ask a question?
Yes, yes.
Michael, it's Dan Karachek. I'm sorry, my video's not working.
Oh,
I've been watching you and Shmuel and your colleagues with great excitement as you move in this direction. And today I'm positively cheering. It's very exciting to see this new work. Can I mention I think it would be only a slight extension for your problem. That would be very, very important as if there were obstacles that are moving and if they were adversarial, of course they could disconnect the space and that would break the fibration assumption. But I'm reasonably sure that if you would be able to put a speed limit on your robot, so for example, instead of looking at the tangent bundle, you looked at a disk bundle or even maybe a sphere bundle, then adversarial motions of the obstacles could effectively disconnect the space without violating your vibration. I'm pretty sure of that. And it begins to look like your ideas and your methods might actually work in this case. This would be extremely important, I think.
thank you, Dan. Yes, you are right. I mean, we are thinking in this direction. And in fact, we have some results. We just published kind of cut. I think I heard it from you actually. Least publishable unit. Remember? Remember?
Oh yeah, I should pay you a visit, Michael. I'm so excited by this work that you guys are. It's very, very exciting work. I'm going to shut up and get out of the way.
No, I just want to say that we cut out part of continuation, and we're still working on continuation of this work. So something in the spirit of what you mentioned, the speed limitations, is partly done, but we're still working on this, and it's very interesting. I agree.
Could I add one thing to what Dan just said? Putting on a velocity limit is an idea. I mean, it's practical, right? So when we do these infinitesimal lifts, then you might get a velocity that's not actually a practical velocity that a autonomous vehicle could achieve. So you have
Yes,
to look at that as well.
yes, you're right. Yeah, absolutely. I mean, we need to put limit on velocities and acceleration,
Yeah.
and yeah. So actually, we have some results already there, but we will publish them separately. But I mean, it's a big subject. It's not
Yeah.
not finished, and we will
Any
think.
other questions?
Yes, I have
Hmm.
two remarks. One, in my opinion, it could be safer not to bet, so to say, on an infinitesimal likely future, but instead on the surely impossible futures, meaning these obstacles in the movements surely have constraints which we might know. And so there are impossible futures, and this would take out whole regions of the configuration space, and this might give a better, a safer project of the movement. The second is a bit military, but I am a reserve officer of the army, so the idea, my idea is that there is a situation in which the movement, the future of the obstacles is absolutely known, and it is when the obstacles aim at you, meaning what you are doing could be extremely important in avoidance strategies when you are attacked by not obstacles but missiles or something like that.
Yeah, very interesting. Yeah, thank you. Nice
Well, in
one.
some sense, that's case two, was it, or something, where you know the future. The future will be that the tracking is on you.
Yeah.
Yeah,
Yeah.
Interesting.
But
Yeah.
this brings up one other point that I would like to know if there are any thoughts about this. So suppose you have your external conditions, but if you assume that you have a fibration, then the fibers are all of the same homotopy type. What happens if a new obstacle comes in? It changes the homotopy type, say, of the fiber. So what type of structure can we have where this happens? Mathematical structure, I mean.
John, you make my life very difficult. This is
That's my
exactly,
job.
yes. Um, well, this is a very good question, and this is exactly what we are thinking about and
Ah,
analyzing. So it's not yet released. So we think in this direction. Yeah,
okay.
it's a very good question, and it's well, it so this formalism doesn't cover the situation.
Mhm.
It's this is a situation which requires slightly more general approach.
Okay, any other questions?
Yes, if I may.
Yes.
And Michael and Stefan, sorry, I owe you an answer, a response to your email where you introduced me to the paper. Um, I wanted to ask if there is any if there is any hope for some sort of classification of reaction forms.
Um,
So classification perhaps is too strong, but can we talk about the dimensionality of the space of reaction forms? So you also are thinking of forms that push away from boundaries. Are there any others? Questions of this kind.
yeah, no, it's a very good question. Just the space of reaction forms is infinite dimensional. I'll just show you. Sorry, where is it? It's infinite dimensional. But you are right that there could be some. I mean, just a moment, I'll find it. Yes, so it is a map. So on each fiber, it's a linear map. No, sorry, I take it
No.
not linear. It's a on each fiber, it's a map, but it's parametrized by the base. So it's definitely infinite dimensional space of reaction forms. But you're right. There is this, as you said, which is absolutely correct. This absolute value, yes, this example is typical. So maybe there is a way of restricting general reaction forms to some restricted class of reaction forms, which are, let's say,
Times functions.
which like Ehresmann connections plus non-linearity like this, absolute value, like absolute value, non. I think it could be the case, but of course it's a guess. It's a guess. It may be true actually. It may be a good point. It can be a good point.
Anything else?
Thank you.
Anyone else? All right, I'm going to stop the recording, but we can keep talking, assuming I know how to stop the recording. Oh, yes.